If a crew launched toward Mars today, the earliest they could expect to be standing back on Earth is somewhere around 3 years from the moment of liftoff. That number catches most people off guard. 3 years is not what the mind reaches for when someone asks how long a space mission takes. People think of Apollo, 8 days door to door. They think of the International Space Station, where a crew rotation takes 6 months and an emergency can have someone home in hours. 3 years belongs to a different category entirely. It belongs to the kind of mission that was science fiction for most of human history and is now only barely within the edge of what is technically imaginable. The instinct is understandable. Mars is a point of light. Spacecraft travel fast. If you can get there, surely you can get back. Point the engine at Earth, fire it, and start moving in the right direction. That reasoning feels solid until you understand that interplanetary space does not work like a road, and Earth is not sitting still waiting for your return. The moment a spacecraft leaves Earth's orbit, it enters a system governed by orbital mechanics, a branch of physics that routinely produces answers the human brain did not expect. Here is the shape of the problem. A return from Mars is not a single journey. It is 3 separate phases locked together by planetary geometry. The first phase is the trip to Mars, which takes roughly 7 months using the most efficient trajectory available. The second phase is the surface stay, which runs somewhere between 14 and 18 months. Not 14 to 18 months of optional exploration, 14 to 18 months of mandatory waiting, during which Earth and Mars move through their orbits until the geometry aligns again for a return. The third phase is the return itself, another 7 months coasting back through interplanetary space. Add those together, and the floor sits just under 3 years. There is no shortcut that current technology can offer for all 3 phases simultaneously, and there is no version of this mission where the surface weight simply disappears. This is the part that stops people. The surface stay is not downtime. It is not a scheduling inconvenience. It is a hard physical requirement written into the orbital mechanics of the solar system, and no amount of engineering can negotiate it away. Earth and Mars are not stationary targets. They are both in motion around the Sun, travelling at different speeds on different orbital paths, and the gap between them changes constantly. When a crew lands on Mars, Earth and Mars will be in a configuration that does not permit a return trajectory for well over a year. The planets have to keep moving until they reach the next alignment window, and that window comes only once every 26 months. Most people have never heard of a launch window. The concept belongs to the world of orbital mechanics, where the specific alignment of 2 planets in their orbits determines whether a transfer between them is even possible. Miss the window for a Mars return, and the next opportunity is 26 months later. There is no alternate route. There is no faster option hiding in reserve. The window closes and the solar system moves on without any regard for the preferences of the crew waiting on the surface below. What makes this question deceptively hard to answer is that the technology involved is almost beside the point for the timeline. A significantly faster rocket would help. Advanced propulsion could shave months off the transit legs. But even with propulsion improvements that do not yet exist in operational form, the surface weight follows its own clock set by planetary geometry, not engine performance. A crew on Mars waits because Earth is not in the right place to receive them, and no rocket solves a geometry problem. The 3-year figure breaks into 3 distinct chunks, and 2 of them involve actually traveling through space. The first chunk is the outbound journey. Using the most efficient path available with current rocket technology, a spacecraft leaving Earth today would take somewhere between 7 and 9 months to reach Mars. Call it 7 months for the optimistic case. The spacecraft is not flying in a straight line. It is coasting along a curved arc through space, following a trajectory calculated to intercept Mars at the precise moment of arrival. That journey by itself is longer than most people expect. 7 months in a metal cylinder, moving away from everything familiar before the mission has even properly begun. The second chunk is the one that surprises people. Once the crew lands on Mars, they cannot leave. Not because the rocket is broken, not because something went wrong. They cannot leave because Earth is not in the right place. The 2 planets are orbiting the Sun at different speeds, on different paths, and the geometry that allows a spacecraft to travel from Mars back to Earth only exists during a narrow window. That window does not stay open. It closes. And the next time it opens is roughly 26 months later. So the crew waits. They wait on the surface of another planet while the solar system slowly rotates into a configuration that will let them go home. That wait lasts a minimum of 14 months and often stretches closer to 18. It is not downtime. It is a hard physical requirement written into the orbital mechanics of the solar system, and no amount of engineering can change it. The third chunk is the return journey. Once the window opens and the crew launches from the Martian surface, they face another 7 to 9 months of coasting through deep space before they reach Earth. The physics of the return works much like the outbound leg. Another long arc, another months-long coast, another period of growing isolation. By the time they splash down or touch down on Earth, the total mission time from launch to landing sits somewhere around 3 years, sometimes slightly under, often slightly over. What makes this hard to absorb is that none of those 3 numbers feel like they should be as large as they are. 7 months to travel to a neighboring planet sounds wrong to anyone who grew up watching spacecraft cross galaxies in films. 14 months of mandatory waiting sounds like a planning failure. 7 months to come home sounds like someone forgot to find a faster route. But all 3 numbers come from the same source. They come from the geometry of 2 planets moving around the same star, and that geometry does not bend for convenience. The surface stay is worth pausing on because it is the most counterintuitive part of the mission. People tend to think of time on another planet as the point of the mission, the payoff for the journey. That framing is not wrong, exactly, but it misses something. The 14 to 18 months on the Martian surface is not a reward for travelling 7 months through space. It is a sentence. The crew arrived at a moment when Earth and Mars were aligned in a way that permitted the outbound trip. The moment they landed, that alignment began shifting. Earth moved ahead in its orbit. Mars moved on its own path. The angle between them changed, and it will keep changing for over a year before it reaches a configuration where a return trajectory becomes possible. There is no shortcut. There is no way to speed up the solar system. The crew waits because the physics demands it. The 26-month gap between return windows is not an arbitrary number. It is the time it takes for Earth to lap Mars and return to a similar relative position. Earth moves faster in its orbit than Mars does, completing a full lap around the Sun in 12 months, while Mars takes nearly 24. The difference in their speeds means that the favourable alignment between them repeats on a cycle, and that cycle runs just over 2 years. Miss the window and the next one is 26 months away. That single fact shapes every decision in Mars mission planning, from how much food to pack to how the rocket that brings the crew home gets fueled. Each of those three phases has its own set of constraints, and none of them can be compressed without consequences that the rest of this video is going to explain in full. The first instinct most people have is that returning from Mars should work the same way leaving Earth does. Point the engine at home, fire it, and start moving in the right direction. It feels obvious. Earth is over there. You are over here. Fire the engine. Go home. This is how driving works. This is how sailing works. This is not how space works. The reason comes down to something most people never have to think about. Everything in space is already moving. Earth is not sitting still, waiting for you to come back to it. Earth is orbiting the Sun at roughly 67,000 miles per hour. Mars is doing the same thing at about 54,000 miles per hour. And the spacecraft sitting on the Martian surface, even while it is not flying anywhere, is also moving, because Mars is carrying it along. When you launch from Mars, you are not starting from a stationary point. You are launching from a platform that is already screaming around the Sun at 54,000 miles per hour. And whatever trajectory you choose has to be calculated with that motion already baked in. Think of it this way. Imagine you are standing on a moving train, and you want to throw a ball to someone standing on a different train moving at a different speed on a parallel track. You cannot throw the ball straight at them. If you do, the ball goes where they were, not where they will be when the ball arrives. You have to aim ahead of them, account for their speed, account for your speed, and release the ball at precisely the right moment. Miss the timing, and the ball lands in empty space. Interplanetary navigation is that same problem, scaled up to planetary distances and orbital speeds, with transit times measured in months rather than seconds. Now add the complication that the two trains are not on parallel tracks. Earth and Mars orbit the Sun at different distances and different speeds, which means the gap between them is constantly changing. At their closest, the two planets are roughly 34 million miles apart. The geometry between them cycles through a full range of positions over a period of roughly 26 months. And the configuration that allows an efficient return trajectory only exists during a narrow slice of that cycle. Outside that window, the geometry is simply wrong. You can fire your engine with everything you have, and you will still arrive at the wrong place at the wrong time. This is the part that trips people up, because it means you cannot simply decide to leave. You cannot look at Earth in the Martian sky and conclude that now seems fine. The decision was made years before you launched, written into mission planning documents by people running orbital mechanics calculations on computers. The departure date from Mars is not a preference. It is a mathematical constraint imposed by the position of two planets moving around the same star. There is another piece of this that makes the intuitive approach even more misleading. When a spacecraft travels from Mars back toward Earth, it does not fly in a straight line. It cannot. A spacecraft that fires its engine and points directly at Earth would need to continuously correct its path for months, burning enormous amounts of fuel with every correction, fighting the gravitational influence of the Sun the entire way. That approach would require fuel quantities that no spacecraft could realistically carry. Instead, what actually works is allowing the Sun's gravity to do most of the work. The spacecraft follows a curved arc, an elliptical path that uses orbital mechanics rather than raw thrust to carry it from one planet to the other. The engine does the hard work at departure, and then the spacecraft coasts. The Sun pulls it through the arc. Months later, If the geometry was right when the burn happened, Earth is exactly where the spacecraft arrives. This is deeply counterintuitive because it means slowing down can sometimes move you outward, and speeding up can pull you inward. It means that to go from a lower orbit to a higher orbit, you fire your engine forward, which seems backward to anyone raised on cars and planes. It means that space travel operates by a set of rules that have very little in common with any form of transportation that humans developed on the surface of a planet. The physics are not complicated once you sit with them, but they demand that every assumption borrowed from everyday experience gets set aside entirely. Earth and Mars are both hurtling around the Sun at tens of thousands of miles per hour, and any path between them has to account for where both planets will be at the moment of arrival, not where they are when you leave. In the 1920s, a German engineer named Walter Hohmann worked out the mathematics of moving between planetary orbits, and every spacecraft that has ever visited Mars has followed the path his equations described. Hohmann was not designing rockets. He was working through a theoretical problem. Given two circular orbits around the same body, what is the minimum energy path connecting them? The answer he found was an ellipse, a single clean arc that touches the inner orbit at one end and the outer orbit at the other. He published the result in 1925. It would be more than 30 years before humanity had rockets capable of flying it. The transfer orbit itself is not intuitive. Most people picture interplanetary travel as pointing a spacecraft at a distant planet and firing the engine until you get there. That is not what happens. When a spacecraft leaves Earth for Mars, it does not aim at Mars. It aims at where Mars will be 7 to 9 months from now. The spacecraft fires its engine once to escape Earth's gravity and shape its trajectory into an ellipse. Then it cuts the engine entirely and coasts. No continuous thrust, no steering, just a curved arc through space, falling around the Sun on a path that was calculated to intersect Mars's orbit at the moment Mars happens to be there. The timing has to be precise. Miss the geometry and you miss the planet. This is the part that stops people. The spacecraft is falling. The entire transit is essentially a controlled fall around the Sun, trading the circular orbit of Earth for an elongated ellipse that stretches outward until it reaches the distance of Mars. At the far end of that ellipse, if the numbers were right, Mars is waiting. The spacecraft does not fight the Sun's gravity to get there. It uses it. The Sun's gravitational field is the highway. Hohmann's insight was that working with that field rather than against it produces the most efficient possible path between two orbits. The numbers that result from this geometry are not arbitrary. They fall directly out of the physics. Earth orbits the Sun at roughly 30 kilometers per second. Mars orbits slower at about 24 kilometers per second because it is farther from the Sun and gravity's pull is weaker there. A spacecraft leaving Earth for Mars has to slow its orbital speed relative to the Sun, counterintuitive as that sounds, to drop into the elongated transfer ellipse that reaches out to Mars's distance. It arrives at Mars moving slower than it started, having traded speed for distance in exactly the way orbital mechanics demands. The outbound journey along this path takes between 7 and 9 months depending on where Earth and Mars are in their respective orbits when the window opens. 7 to 9 months is not an engineering failure. It is the geometry's answer. You could build a more powerful rocket, carry more fuel, and push a spacecraft along a more direct path, but that path would cost exponentially more energy and still take months. The Hohmann transfer sits at the minimum of the energy curve. everything faster than it requires progressively more fuel for progressively smaller gains in time. This is why every robotic mission ever sent to Mars, Mariner, Viking, Pathfinder, Curiosity, Perseverance, followed a path that Hohmann would have recognized. The spacecraft change, the propellants change, the destination does not, and neither does the geometry connecting it to us. The elegant detail is what happens at the end of the arc. When the spacecraft reaches Mars's orbital distance, it is moving at a speed that happens to match the velocity needed to enter orbit around Mars or adjust for a landing trajectory. The physics align. The arc delivers the spacecraft at the right distance, moving at roughly the right speed, because that is exactly what an ellipse connecting two orbits is designed to do. There is no coincidence here. The math was always going to produce this result. For a return journey, the same logic applies in reverse. A spacecraft leaving Mars fires its engine to drop its orbital speed further, shaping a new transfer ellipse that falls inward toward Earth's orbit. The Sun's gravity accelerates it on the inbound leg, and after another 7 to 9 months of coasting, the spacecraft reaches Earth's orbital distance. The trip home takes as long as the trip out, not because of any engineering limitation, not because the spacecraft is exhausted, but because the orbit connecting the two planets has a fixed length and the spacecraft travels it at speeds set by physics rather than preference. The Hohmann transfer is not an engineering choice that someone could eventually replace with a better design. It is the minimum energy solution to a geometry problem, and geometry does not negotiate. Every 26 months, Earth and Mars line up in a configuration that makes a Hohmann transfer between them possible. Not every month, not every year. Every 26 months, and the window stays open for only a matter of weeks before the geometry shifts and the opportunity closes. This is not an engineering limitation. It is a consequence of the two planets orbiting the Sun at different speeds, and no amount of rocket power changes it. Earth completes one orbit in 365 days. Mars takes 687. Because they are moving at different rates, the angle between them is always shifting. For a Hohmann transfer to work, Mars has to be positioned slightly ahead of Earth at the moment of departure, so that by the time the spacecraft coasts along its long elliptical arc and reaches Mars's orbital distance, Mars has moved forward enough to be there waiting. That alignment occurs roughly every 779 days, a little over 2 years. Miss the window and Mars is in the wrong place. Fire the engines anyway, and the spacecraft arrives at Mars's orbital distance with no Mars in sight. This is what makes the 26-month cycle so consequential. It is not a scheduling inconvenience. It is the fundamental clock that governs all of interplanetary travel, and every decision in a Mars mission traces back to it. When NASA sent Curiosity to Mars in 2011, ESA and Roscosmos sent the ExoMars Trace Gas Orbiter in 2016, and when Perseverance launched in 2020, each of those missions launched within a compressed window of weeks. The reason every major Mars mission in history seems to cluster together is not coincidence or competition. It is physics. Every space agency on Earth is targeting the same narrow slice of geometry because it is the only slice available. The launch window that opened in the summer of 2020 was used by NASA, China, and the United Arab Emirates simultaneously. 3 spacecraft from 3 countries left Earth within days of each other. They all arrived at Mars within weeks of each other. The window does not care about national programs or political calendars. For a crewed mission, the The stakes of this cycle are difficult to overstate. The window that allows departure from Earth also determines months in advance when the crew will arrive at Mars and when the return window will eventually open. These are not independent decisions. The outbound launch date, the surface stay duration, and the return departure date are all locked together by the same orbital arithmetic before a single person boards the spacecraft. Mission planners work backward from the return window to determine everything else. The 26-month cycle shapes the design of every consumable on a Mars mission. If a crew is going to spend 14 to 18 months on the surface waiting for the geometry to align, then the mission has to carry or produce enough food, water, oxygen, and medical supplies to sustain them through that entire period with margin to spare. A crew cannot simply pack lighter if the surface stay is planned to be shorter. The stay is as long as the planets dictate, and the supplies have to match. This means the mass budget for a crewed Mars mission is enormous, and the window that determines when the crew leaves Earth also determines how much they have to bring. Cargo missions face the same constraint. If an uncrewed supply delivery misses its launch window, the cargo sits on the ground for another 26 months. The pre-positioned habitat, the fuel production equipment, the return vehicle, all of it has to reach Mars on a schedule synchronized with the same planetary clock. A missed cargo window does not just delay a delivery, it delays the entire human mission by 2 years, because the crew cannot safely depart Earth until those systems are confirmed operational on the Martian surface. There is something clarifying about this constraint once you understand it fully. The question of when to go to Mars is not decided by a committee or a budget cycle. It is decided by a clock that has been running since the solar system formed, ticking off its 26-month intervals without regard for anyone's timeline. Engineers can optimize the spacecraft. They can improve the propulsion. They can reduce the mass or increase the reliability. What they cannot do is move the window. The geometry opens when it opens. Miss that window, and the next one is 26 months away, a delay that compounds every other problem a crew on the Martian surface is already dealing with. For the first few days after leaving Earth orbit, the crew of a Mars-bound spacecraft would still be able to see our planet clearly, a blue and white sphere shrinking behind them as the distance grew. Within a week, Earth would look like a bright star. Within a month, it would be difficult to pick out from the surrounding field of stars without knowing exactly where to look. This is how the journey begins, not with drama, but with distance accumulating quietly in every direction. The spacecraft itself leaves Earth orbit at roughly 11 kilometers per second relative to the Sun. Then the engines cut. That is the part most people do not expect. For the next 7 months, there is no engine firing, no continuous thrust pushing the vehicle forward. The spacecraft coasts. It rides the arc of a Hohmann transfer ellipse through interplanetary space, following a path that was calculated long before launch, and the physics of orbital mechanics carry it the rest of the way. There is almost nothing for the propulsion system to do until Mars orbit insertion. The ship is not flying so much as falling along a precisely shaped curve through 300 million miles of empty space. Interplanetary space is not what most people picture. There are no asteroid fields to dodge, no visible nebulae painting the windows. There is nothing. The distances between objects in the solar system are so vast that the spacecraft travels in essentially featureless blackness for months at a time, with the sun growing slightly smaller and dimmer as the distance from it increases. The stars do not move. The background does not change. Nothing outside the windows gives any sense of motion at all, even though the spacecraft is moving at tens of thousands of miles per hour. Inside, the crew is confined to a volume roughly comparable to a small apartment, shared among 4 to 6 people for the duration. Every cubic meter has been assigned a purpose. Exercise equipment takes up space that could have gone to supplies. Supplies take up space that could have gone to living area. The romance of space exploration tends to involve windows and vast views. The reality involves schedule adherence, equipment maintenance, carefully rationed food, and the psychological weight of knowing that the nearest other human beings are already tens of millions of miles away. Communication with Earth degrades steadily as the mission progresses. In the first weeks, a signal takes only a few minutes to reach Earth and return. By mid-journey, the one-way delay has grown to 10 or 15 minutes. A simple conversation becomes impossible. Mission control can send instructions and the crew can respond, but the exchange plays out over 30 minutes or more of waiting. As the distance grows, the crew becomes functionally autonomous in a way that no other human spaceflight has ever required. Decisions that on the space station would involve a quick consultation with engineers in Houston have to be made alone, with whatever information is already on board. Meanwhile, the bodies of the crew are adapting to weightlessness in ways that work against them. Bone density begins declining almost immediately. Without gravity loading the skeleton, the body sees no reason to maintain the same bone mass it needed on Earth. Muscles atrophy on a similar timeline. Fluid shifts toward the head, creating pressure changes that affect vision in a significant fraction of long-duration astronauts. The cardiovascular system loses conditioning. These changes have been documented thoroughly on the International Space Station, where missions typically run 6 months, almost exactly the length of this transit. The difference is that station crews return to Earth when their mission ends. A Mars-bound crew arrives at their destination in this condition and immediately faces the demands of operating in Martian gravity for over a year before they can begin recovering. None of this is unknown or unexpected. Mission planners account for it. Exercise protocols take up 2 hours of every crew day specifically to slow the physiological deterioration. Nutrition is managed carefully. Countermeasures developed over decades of space station research are applied throughout the transit. But slowing the decline is not the same as preventing it. 7 months in weightlessness leaves a mark on the body regardless of how diligently the crew exercises. By the time Mars fills the windows, the crew has already spent 7 months in space, absorbed the first major portion of their radiation dose, and lost enough bone density that their bodies will need months to recover. Getting to Mars is only half the problem, and in some ways the easier half. After 7 months of coasting through interplanetary space, the spacecraft finally closes on Mars. From a distance, the planet looks smaller than most people expect. A pale, rust-colored disk, quiet and still against the black. Then entry begins, and nothing about it is quiet. The process is called EDL, Entry, Descent and Landing. It is the most compressed and dangerous sequence in the entire outbound mission. The spacecraft hits the Martian atmosphere at roughly 20,000 kilometers per hour. A heat shield takes the first blow, temperatures climbing to over 1,600 degrees Celsius as the thin atmosphere claws at the vehicle. For several minutes, the crew cannot communicate with Earth. The signal is blocked by the plasma sheath forming around the ship. Earth will not know the landing succeeded until the news travels across hundreds of millions of miles at the speed of light. a delay of anywhere from 3 to 22 minutes depending on where the planets are in their orbits. Mars makes this harder than it sounds. The atmosphere is only about 1% as dense as Earth's, which means it generates just enough friction to heat the shield dangerously, but not nearly enough to slow the vehicle to landing speed on its own. The Moon has no atmosphere at all, so you use rockets the entire way down. Earth has a thick atmosphere, so parachutes do most of the work. Mars falls into a miserable middle ground. A parachute alone cannot stop a spacecraft heavy enough to carry a crew. Rockets alone burn too much fuel. The solution is a choreographed sequence of all of it: shield, parachute, powered descent, executed in the span of minutes with no margin for error and no opportunity for the crew to ask Earth for advice mid-sequence. Every decision that matters has been pre-programmed or made on the spot by the crew itself. Then the lander touches down, the dust settles, the mission has arrived, and immediately the central problem of the entire mission makes itself known. The return window is not open. It will not open for roughly 14 to 18 months. There is no way to go home. This surprises people when they first understand it. The instinct is to imagine a spacecraft like a car. You drive somewhere, you turn around, you drive back. But Earth has not been waiting in place. For the entire 7 months the crew was in transit, Earth kept moving along its own orbit. By the time the spacecraft reaches Mars, Earth and Mars are positioned in a way that makes a return trajectory physically impossible without enormous amounts of fuel that no mission carries. The geometry is simply wrong. The angle between the two planets, their relative velocities, the arc any return spacecraft would have to follow, none of it aligns into a workable path for more than a year. The window will open again. The math says so with precision. Earth and Mars will eventually reach a configuration where a Hohmann transfer back is possible. And when that happens, the return trajectory becomes efficient and achievable with the fuel the Mars Ascent Vehicle carries. But that moment is not now. It is not close. The crew landed knowing this. Mission planners designed around it from the beginning. The surface stay is not a contingency. It was always the plan. That does not make it easier to sit with. The crew is on another planet, separated from Earth by distances that expand and contract on a timetable no one can alter. At its greatest separation during the surface stay, Mars and Earth will be nearly 400 million kilometers apart. A radio signal takes over 20 minutes to cross that distance one way. A conversation with anyone on Earth involves a 40-minute wait between question and answer. There is no rescue possible. There is no early departure. The orbital mechanics that made the outbound journey efficient now hold the crew in place as firmly as any wall. The 14 to 18 months ahead are not empty time. Scientists designed the surface program to make use of every day. There is genuine work to do. Geological surveys, atmospheric measurements, equipment tests that matter for future missions. But underneath all of it, running like a clock that cannot be stopped, is a countdown to the only thing that actually sends the crew home. Earth and Mars, moving steadily through their orbits, inching toward the alignment that opens the return window. The moment the lander touches down, the mission clock resets and the crew enters a new phase. Not exploration, not science, not adventure in any simple sense, but waiting for the geometry of the solar system to allow them to go home. The 14 to 18 months a crew must spend on Mars before returning home is not a planning choice that future engineers can engineer around. It is a consequence of orbital mechanics, and orbital mechanics does not respond to budgets or timelines or the psychological state of a crew sitting on a red planet waiting for geometry to shift in their favor. The moment the lander touches down, Earth and Mars are already moving apart. That gap will widen for months before it begins to close again into the configuration that makes a return trajectory possible. There is nothing a crew can do to accelerate that process. They simply have to wait. To understand why the wait is so long, you have to hold two moving objects in your mind simultaneously. Earth completes one orbit around the Sun in 365 days. Mars takes 687. Because the two planets move at different speeds, their positions relative to each other are constantly shifting. A spacecraft leaving Mars on a Hohmann transfer needs to depart at a moment when Earth is positioned far enough ahead in its orbit that the arc of the return trajectory will intercept it after roughly 7 months of coasting. That window is narrow. It occurs roughly every 26 months. When a crew arrives at Mars, that window has just closed behind them. The geometry that allowed the outbound journey has passed. The geometry that will allow the return has not yet formed. Between those two moments lies the surface stay. The minimum surface stay works out to somewhere between 14 and 18 months, depending on exactly when in the 26-month cycle the mission launches. Some launch windows produce shorter stays. A crew that arrives at Mars near one end of the optimal outbound window may face 18 months on the surface before the return alignment forms. A crew that arrives near the other end may get away in 14. Neither figure is short. Both figures are hard floors set by the positions of two planets that have no interest in human convenience. What makes this psychologically difficult is not just the length of the wait, it is the precision of it. The crew knows, within a margin of a few weeks, exactly how long they are staying. There is no possibility of rescue before that window opens. There is no abort option that brings them home in any reasonable time frame. A medical emergency, a mechanical failure, an interpersonal breakdown, none of these change the date on the calendar when the return window becomes viable. The crew moves on that schedule too, whether they want to or not. Mission psychologists who have studied long-duration isolation consistently point to the known endpoint as a double-edged feature of Mars missions. It gives the crew something to count toward. It also means they can calculate exactly how many days remain on any given morning, which is its own particular weight to carry. Mission planners have always understood this, and they have always designed around it. The surface stay is not dead time. It is the science mission. Mars has been visited by dozens of robotic probes, and not one of them has told us everything we need to know about the planet's geology, its subsurface water ice, its ancient river systems, its potential for past or present microbial life. A crew with 16 months and the dexterity of human hands can accomplish what decades of robotic exploration cannot. Samples can be collected from dozens of locations. Drill cores can reach depths that no robotic instrument has yet accessed. Experiments requiring real-time human judgment can be run continuously. The surface stay is, from a scientific standpoint, the entire reason for going. Everything else, the rockets, the trajectories, the life support, exists to put humans on that surface for that length of time. But the science does not make the wait feel shorter. The Martian surface provides no psychological relief that resembles anything familiar. The sky is the wrong color. The horizon is closer than it looks. The dust is fine enough to coat everything and abrasive enough to destroy seals over time. The temperature swings between tolerable and lethal within the same day at certain latitudes. Every excursion outside the habitat requires a pressure suit and a checklist and a level of discipline that does not ease with familiarity. The crew is never not working, and the crew is never not aware of how far they are from Earth. Near opposition, it can appear as a bright bluish star, but for much of the stay it is lost in the sun's glare entirely. Communication delays run between 3 and 22 minutes each way, depending on planetary geometry. A conversation with a family member is not a conversation. It is an exchange of messages separated by the better part of an hour. The psychological isolation is not metaphorical. It is structural. When the return window finally opens, the crew will have spent over a year on a planet with a toxic atmosphere, no magnetic field worth speaking of, and radiation levels that make a long Antarctic winter seem comfortable. Mars gravity is roughly 38% of what you feel standing on Earth, which sounds manageable until you realize that the human body was not designed to function in it for 18 months. The Apollo astronauts spent days on the moon in 1/6 gravity and came home with data that told scientists something important. Short stays are survivable. 18 months is not a short stay. The scale changes everything. What the body tolerates for a few days, it quietly dismantles over a year and a half. The process starts almost immediately after landing. Bone mineral density begins dropping within weeks of reduced gravitational loading. Muscles that spend their entire existence on Earth fighting a 1G field no longer need to work as hard, and the body, which wastes nothing it does not need, begins stripping them down. The legs go first and fastest, postural muscles thin. The cardiovascular system, which on Earth pushes blood upward against gravity constantly, recalibrates to a world that demands less of it. None of this is dramatic in the short term. None of it is visible. It accumulates in the background while the crew runs experiments and checks equipment and eats their meals and tries to sleep. There is science to do, which matters both for the mission and for the crew's mental state. A surface stay of 14 to 18 months gives a team of astronauts more time on Mars than every robotic rover combined has spent conducting meaningful exploration. They would drill into the subsurface. They would collect samples from sites that no remote-controlled machine could reach. They would study the weather, map the geology, run biological experiments in the habitat. The work is real and the work is important, but underneath all of it is an awareness that cannot be fully switched off. The return window is months away. The spacecraft that will carry them home is sitting on the surface nearby, and there is nothing to do but wait for the solar system to rotate into the right configuration. Radiation does not pause while they wait. The surface of Mars offers more protection than the transit phases of the mission, but it is not Earth. Mars has no global magnetic field. Its atmosphere is thin, roughly 1% of Earth's at sea level, which absorbs some incoming particles but stops nothing like what our own sky blocks. Galactic cosmic rays stream through the Martian surface constantly. Solar energetic particle events, which can deliver dangerous doses in a matter of hours, require the crew to shelter in place in the most heavily shielded section of the habitat. Every day on the surface adds to a cumulative radiation account that will not be paid until years later in the form of elevated cancer risk. The crew knows the numbers. Mission planners calculated them before departure. Knowing the numbers does not make them easier to carry. The psychological environment is its own separate challenge. The crew is confined to a habitat on a planet with no breathable air outside the walls. Every excursion in a pressure suit carries risk. The communication delay to Earth runs between 3 and 22 minutes each way, depending on where the two planets are in their orbits, which means real-time conversation with anyone back home is impossible. A question asked takes at minimum 6 minutes to receive an answer, often far longer. Over 18 months, that delay does not become normal. It becomes a persistent reminder of how far from home the crew actually is. Mission support teams on Earth work to counteract this with scheduled contact windows, psychological support protocols, and carefully designed mission timelines that give the crew agency and purpose. The research on long-duration isolation from Antarctic stations and space station missions informs all of it. It helps. It does not solve the fundamental problem. By the midpoint of the surface stay, the crew's bodies have diverged from baseline in measurable ways. Bone density scans would show losses of several percent. Muscle mass in the lower body would be reduced. Fluid shifts that occur in low-gravity ultravision in some individuals, a phenomenon documented extensively on the space station and not yet fully understood. The cardiovascular changes that seemed minor at first have compounded. None of this is catastrophic. The crew is functional, working, capable, but they are not the same people who landed, and the gap between who they were and who they are now will only widen before it begins to close. By the time the return window opens, the crew going home will be physically different people from the ones who landed, weaker in some ways, adapted to a world that is about to become hostile to them again in entirely new ways. Launching from Mars to begin the return journey requires a dedicated rocket called the Mars Ascent Vehicle, and that rocket has to be waiting on the surface, fueled and functional, before the crew ever leaves Earth. This is not a detail, it is the central constraint around which everything else in the return mission is designed. The MAV arrives at Mars on its own, years before any crew does, delivered by an uncrewed cargo mission that has to survive entry, descent, and landing without any human hands to correct a problem. By the time the crew touches down, the MAV has been sitting on the Martian surface for a year or more, exposed to dust storms, thermal cycling between extreme cold and extreme heat, and radiation that degrades electronics over time. Before the crew even begins counting down to launch, they have to verify that everything still works. Mars has roughly 38% of Earth's surface gravity. That sounds forgiving. In practice, it still means a rocket must accelerate hard enough to reach orbital velocity, which for Mars is approximately 3.5 kilometers per second. That is slower than Earth's orbital velocity of about 7.9 kilometers per second, but it is still a genuine orbital insertion burn, not a gentle hop. Mars also has an atmosphere, thin as it is. That atmosphere creates aerodynamic drag during the early phase of ascent, which forces the vehicle to burn fuel-fighting resistance before it even reaches the altitude where the atmosphere stops mattering. The physics are less brutal than launching from Earth, but they are not trivial. The MAV cannot afford to be underpowered. The fuel situation adds another layer. A fully fueled MAV launched from Earth and landed on Mars is carrying an enormous mass penalty through every phase of the mission. The more appealing option, and the one most mission architectures now assume, is that the MAV arrives empty and is fueled on Mars using propellant manufactured from local resources. Liquid oxygen can be extracted from carbon dioxide in the Martian atmosphere. Methane can be synthesized through a chemical process using that same atmospheric CO2 and hydrogen brought from Earth, or extracted from subsurface ice. This approach dramatically reduces the mass that has to be launched from Earth in the first place. But it means the fuel production equipment has to have been running successfully for months before the crew ever considers climbing into the ascent vehicle. If the propellant tanks are not full when the return window opens, the mission is in serious trouble. The return window itself does not stay open indefinitely. There is a period of weeks, roughly 2 to 3 months, during which the orbital geometry between Mars and Earth permits a Hohmann transfer back. Inside that window, specific departure dates produce different travel times and different fuel requirements. Mission planners select a target date well in advance. The crew knows that date. Everything in the weeks leading up to it is oriented toward being ready. Launch day on Mars would look nothing like a launch from Earth. There is no crowd. There is no launch tower in any conventional sense. The Mayav sits on the surface, likely at a site chosen for flatness and proximity to the base, and the crew boards it after weeks of preparation and system checks. When the engine ignites, the ascent is fast and steep. Mars's thin atmosphere means less aerodynamic concern at higher altitudes, and the vehicle climbs through a pale reddish sky that transitions quickly to the dark of space. The entire ascent to low Mars orbit takes only a few minutes. Wrong physics, wrong intuition. It feels anticlimactic compared to the scale of what it represents. This is the highest risk single event in the entire return process. The reason it carries that distinction is simple. There is no abort. If the engine fails to ignite cleanly, or if it shuts down prematurely before reaching orbital velocity, there is no recovery. The crew cannot return to the surface safely. There is no rescue mission staged somewhere in Mars orbit waiting to come down. Everything that comes before, the 14 months of waiting, the science, the physical deterioration, the preparation, rests on this single burn performing exactly as designed. Once in orbit, the vehicle has to find its transfer spacecraft. The rendezvous requires precise timing and careful navigation, matching orbits with a vehicle that has been waiting in Mars orbit for months. Small errors in orbital insertion can turn a straightforward rendezvous into an extended chase. Once the docking is confirmed and the crew transfers, the MAV is left behind. Once in Mars orbit, the crew either boards a waiting transfer spacecraft or begins the return journey directly, depending on the mission architecture. But either way, the long coast home has begun. The return journey from Mars to Earth takes roughly the same amount of time as the outbound leg, somewhere between 6 and 9 months depending on when the window opens and which trajectory the mission uses. This surprises people. The intuition is that going home should somehow be faster. The destination is known, the route has been travelled, and there is presumably some urgency driving the crew back toward Earth. None of that changes the physics. The spacecraft is not driving down a highway where a faster speed simply shortens the trip. It is falling through gravitational geometry, following a curved arc that the sun's own gravity defines, and that arc has a fixed duration regardless of how much anyone aboard wants it to be shorter. The return transfer orbit is another ellipse, shaped much like the one that carried the crew to Mars. One end of that ellipse touches the orbit of Mars at the moment of departure. The other end intersects Earth's orbit at the moment of arrival. The spacecraft is not thrusting the whole way. It fires its engines to leave Mars orbit, establishes the trajectory, and then coasts for months. The engines do very little after that initial burn, and the timeline is set from the moment of departure. There is no throttle to push. There is no shortcut through the middle. The reason the return takes as long as the outbound leg comes down to the same problem Hohmann identified a century ago. A Hohmann transfer orbit is the minimum energy path between two circular orbits. Minimum energy means minimum fuel, and minimum fuel is not optional when everything the mission carries had to be launched from Earth or manufactured on Mars. Trading fuel for speed is always available in principle. It costs enormously in mass, and the math on that trade turns punishing very quickly. The result is that the standard return arc, optimized for fuel rather than time, runs roughly 7 months. That number is not an artifact of outdated technology. It is what the geometry of two orbits, separated by tens of millions of miles, allows under the constraint of keeping propellant requirements within the bounds of what a spacecraft can actually carry. Some mission architectures stretch the return beyond 7 months. If the window that opens on Mars places Earth and Mars in a configuration that only allows a longer arc, the crew takes a longer arc. Some return windows produce trajectories of 8 or 9 months. Some of the more favorable alignments allow 6. The crew does not choose from a menu. The orbital mechanics select the trajectory, and the crew is along for the ride. Throughout this return coast, Earth grows in the windows slowly. For the first weeks, it is indistinguishable from any other point of light. After 2 months, a good camera can resolve it as a disk. After 4, it starts to look familiar. After 6, the blues and whites of continents and weather systems become distinct. The crew has been watching this for months before the planet is actually close enough to matter. That prolonged approach is its own kind of psychological experience. The destination is visible, and it remains unreachable for most of the journey. Communication delays persist throughout the return. In the early weeks after leaving Mars, the signal delay between the spacecraft and Earth is still measured in tens of minutes. As the distance closes, that delay shrinks, but it never disappears during transit. The crew is still operating with the functional independence of people who cannot reach anyone in real time. Earth is getting closer without feeling close. The physical reality of the return transit is that the crew is weightless again. After over a year in Martian gravity, even at 38% of Earth's pull, returning to zero gravity means the body begins adapting in all the wrong directions once more. Fluids shift toward the head. Muscles trained to function in some gravitational environment must now relearn microgravity. Bone density, already compromised by months on Mars, faces additional stress. The crew is not coasting home in good condition. They are coasting home while their bodies continue to change in ways that will make arrival on Earth significantly harder. The emotional weight of the return carries its own specific texture. The outbound journey had the energy of going somewhere new, the anticipation of a destination no crew had ever reached. The return has neither of those. The destination is familiar. The journey ahead is already understood in full. The crew knows what 7 months in a confined spacecraft feels like, because they have done it before. They know how long the days are, how repetitive the routine becomes, how deeply the isolation compounds over time. For the crew, the return is in some ways harder than the outbound leg. The novelty is gone, Mars is shrinking behind them, Earth is still months away, and they are carrying the cumulative physical and psychological weight of everything that came before. A spacecraft that has spent over a year in the Martian environment is not the same machine that left Earth. The dust alone does that. Mars is a world defined by its dust, fine electrostatically charged particles that work into seals, coat solar panels, infiltrate mechanical systems in ways that engineers spend years trying to anticipate. A vehicle sitting on the surface for 14 to 18 months absorbs that environment into every exposed component. Thermal cycling does the rest. Martian nights drop to temperatures cold enough to crack materials that performed perfectly in the warmth of the day. Every dawn brings another expansion, every night another contraction. After hundreds of cycles, metal fatigues, seals degrade. Tolerances that were measured in fractions of a millimeter on the assembly floor have shifted in ways that are difficult to detect until something stops working. The return vehicle is not necessarily the same vehicle that landed. Mission architectures separate the lander from the ascent stage and the transfer spacecraft. The transfer craft may have been waiting in Mars orbit rather than sitting on the surface. The spacecraft's external surfaces, thermal blankets, sensors, optical systems, have been absorbing that radiation for over a year. Atomic oxygen is less of a concern at Mars than in low Earth orbit, but high-energy particles leave their mark on electronics over time. Components rated for a 5-year service life have consumed a significant fraction of it before the return leg even begins. Navigation during the return demands precision that has no margin for complacency. The spacecraft is not flying toward a stationary target. Earth is moving, and the trajectory has to be aimed not at where Earth is, but at where Earth will be when the spacecraft arrives 7 months later. Small deviations in the departure burn, errors of a fraction of a percent, compound over hundreds of millions of miles into targeting errors large enough to miss entirely. Course corrections can compensate, but each correction consumes propellant, and the propellant budget for the return is not generous. Engineers at Mission Control calculate the return trajectory months in advance and continue refining it throughout the journey. But every instruction they send faces a delay that makes real-time control impossible. That communication delay is one of the more disorienting facts about interplanetary travel. At the moment the return begins, Earth and Mars may be separated by enough distance that a radio signal takes 15 to 20 minutes to cross the gap. A crew that notices a problem, radios Earth for help, waits for a response, is looking at a minimum 30 to 40 minutes before any guidance arrives. In that time, a cascade failure in a critical system can evolve far beyond its starting point. Mission controllers on Earth can monitor telemetry and model solutions, but the people who have to act on those solutions are the ones in the spacecraft, working from whatever knowledge and supplies they have on board. The crew is not helpless. They are trained engineers and physicians, but they are isolated in a way that no other operational environment in human history has replicated. This isolation shapes how the spacecraft is designed and how its systems are managed. Redundancy is built into every critical function. Life support does not run on a single system. It runs on 2, sometimes 3, each capable of maintaining the crew independently. Navigation runs the same way. Power generation, water reclamation, atmospheric processing, all of it is layered with backups whose whole purpose is to survive the failure of whatever is upstream. But redundancy has limits. A backup system that was installed 18 months ago and has been operating continuously in a high radiation environment carries its own wear history. The backup is not new. It is merely the system that has failed less. There is something almost unnerving about the arithmetic of it. The spacecraft leaves Mars carrying the accumulated wear of the entire mission so far. Every seal, every pump, every circuit board, every structural joint has a service history behind it, and ahead of it lies another 7 months of thermal cycling, vibration, radiation, the mechanical demands of continuous life support. Engineers design to margins that account for this. They model failure rates and run probability analyses that are intended to ensure the vehicle survives. The numbers are reassuring on paper. Every system on the return vehicle, life support, propulsion, navigation, communication, has to work reliably for 7 more months in an environment where the nearest repair facility is measured in light minutes. A spacecraft arriving from Mars does not gently settle into Earth's atmosphere the way a capsule returning from the space station does. A station capsule re-enters at roughly 7.8 kilometers per second. A vehicle arriving from Mars is moving faster than that, considerably faster, because it has been falling inward toward the Sun for months and arrives at Earth with excess velocity that the planet's gravity pulls even higher. Entry speeds of 12 to 15 kilometers per second are the realistic range for a standard Hohmann return. The atmosphere has to kill that speed. There is no other option. Chemical braking burns too much fuel, and by this point in the mission there is no fuel to spare. The air itself is the brake. What that means physically is this: when the capsule hits the upper atmosphere at those speeds, the air in front of it cannot move out of the way fast enough. It compresses. Compressed air heats. The temperatures in the shock layer in front of the heat shield reach somewhere between 2,000 and 3,000 degrees Celsius. This is not the temperature of the shield itself. It is the temperature of the gas around it. The shield absorbs a fraction of that. Still, materials on the leading face reach temperatures that would vaporize most metals. The shield ablates deliberately, sacrificing its outer layers to carry heat away from the structure behind it. This is the engineering solution: controlled destruction of the heat shield surface in exchange for survival of everything inside. The crew experiences this as deceleration. Peak G-forces during a Mars return entry run somewhere between 4 and 6 G, meaning a person who weighs 80 kilograms suddenly weighs 320 to 480 kilograms for the duration of peak heating. That lasts minutes. This is not the gentle 1.5 to 2 G that station crews feel on their way home. Station crews re-enter after 6 months in weightlessness and still require assistance walking off the capsule. The crew returning from Mars has spent 7 months in transit, over a year in Martian gravity, which is 38% of Earth's, and then another 7 months falling through space. Their bones have lost density, their muscles have atrophied, their cardiovascular systems have adapted downward. The body returning from Mars is not prepared for 4G. The bones are not the bones that left. Mission planners account for this with crew positioning. Lying flat, perpendicular to the direction of deceleration, distributes the load across the body rather than stacking it onto legs and spine. Even so, the compressive force on a skeleton that has been unloaded for the better part of 3 years is a serious medical concern. Fractures during re-entry have never happened on a human spaceflight mission, but no human has ever re-entered from a Mars transit. The margin is thinner than it was for any previous mission. The station analogy only goes so far, and then it stops being useful. Beyond the crew, the vehicle itself is entering the atmosphere after more than 2 years in service. The heat shield was installed on Earth, shipped to Mars orbit, and has been through thermal cycling, micrometeorite exposure, and the Martian dust environment. Pre-entry inspection is limited to what sensors and cameras can see. If the shield has any degradation, any thinning in a section, any gap in its protective surface, the crew does not know that until the peak heating phase begins. Communication during the blackout period, roughly 10 minutes when the plasma around the capsule blocks radio signals, is impossible regardless. Mission control cannot help. What was built has to hold. Faster return trajectories sharpen every one of these problems. The 2031 configurations that researchers have identified bring the spacecraft back to Earth at 15 kilometers per second or higher. The 56-day outbound trajectory pairs with a return velocity that pushes the boundaries of what any tested heat shield material can manage. Existing ablative materials have been validated against certain temperature ranges and certain flux rates. Beyond those limits, the data thins out. Engineers can model what happens. They can run simulations. What they cannot do is point to a shield that has been built, tested at those conditions, and certified for a human crew. The gap between what the fast trajectories require and what exists in a warehouse is not a small one. The faster the return trajectory, the hotter and more violent the re-entry, which is why every proposal to speed up the journey home also requires heat shields that do not yet exist in operational form. Of all the ways the return journey from Mars can hurt a crew, radiation is the one that builds silently throughout every day of transit and leaves no immediate symptoms. There is no pain, no fever, no signal from the body that anything has gone wrong. The damage accumulates at the cellular level, in the DNA of dividing cells, in the tissue of organs that will not register the injury for years or decades. By the time a crew member boards the return spacecraft at Mars and begins the 7-month coast back to Earth, the radiation clock has already been running for over a year. The outbound journey deposited its dose, the surface stay deposited more, and now the return leg adds the final portion of an exposure that cannot be undone. The radiation environment of interplanetary space is different from anything experienced in Earth orbit. The International Space Station sits inside Earth's magnetic field, which deflects a significant fraction of the charged particles streaming in from deep space. Step beyond that field into the open space between planets, and two distinct threats emerge. The first is galactic cosmic rays. These are not solar radiation. They originate from sources outside our solar system. Collapsed stars, supernova remnants, energetic processes billions of light years away, and they arrive continuously from every direction at velocities approaching the speed of light. They are not particles you can easily block. A galactic cosmic ray nucleus, particularly a heavy one like iron, carries enough energy to pass through centimeters of aluminum as if the metal were not there. It ionizes tissue along the way. It produces secondary particles that spread the damage outward. The shielding that protects against ordinary radiation does almost nothing against the highest energy galactic cosmic rays, and in some cases, thicker shielding actually makes the secondary particle problem worse. The second threat is solar energetic particle events. These are sudden. The sun periodically releases bursts of high-energy protons associated with solar flares and coronal mass ejections, and a major event can deliver a dangerous dose within hours. Unlike galactic cosmic rays, solar energetic particles can be partially shielded against. A well-designed storm shelter with dense shielding can reduce the dose significantly. But the warning time is short, the events are not fully predictable, and the doses from a major event without adequate shelter can reach levels that cause acute radiation sickness. A crew on the return transit has to treat every significant solar event as a potential emergency. What makes the transit phases so critical is the comparison to the surface. Mars has almost no magnetic field. Its atmosphere is roughly 1% the density of Earth's at sea level. Neither provides meaningful protection against galactic cosmic rays. But the planet itself does something useful. Standing on the Martian surface, the ground blocks radiation coming from below. The terrain provides partial shielding from half the sky simply by being there. This is enough to make a measurable difference. Measurements from instruments aboard Mars spacecraft, including data gathered during the Curiosity rover's journey to Mars, suggest that the transit to and from Mars accounts for the majority of the total mission radiation dose, even though the transit phases are shorter than the surface stay. The surface provides incomplete but real protection. Deep space provides none. The numbers give this shape. Studies examining realistic crewed Mars trajectories project transit radiation doses in the range of 331 millisieverts, plus or minus around 54 millisieverts for a combined outbound and return journey. To put that in perspective, the average American receives roughly 3 millisieverts per year from all sources combined. The NASA career limit for astronauts has historically been set to keep the estimated lifetime cancer risk increase below 3%. At 331 millisieverts of transit dose, the estimated cancer risk increase is roughly 4% for a middle-aged adult, depending on age at exposure, sex, and individual biology. Here is where the physics produces a result that runs against instinct. Faster return trajectories reduce the cancer risk, not marginally, significantly. Cutting the return journey from 7 months to 3 months means 3 fewer months of continuous galactic cosmic ray bombardment in open space. If a more aggressive trajectory, one of the 2031 configurations described earlier, for instance, reduces the combined transit time, it also reduces the total deep space radiation dose. The analysis comparing standard trajectories to faster alternatives shows the estimated cancer risk dropping from roughly 4% to approximately 1.5%. Speed, in this case, is not just a convenience. It is a genuine medical argument. The uncomfortable implication is that the conservative, fuel-efficient Hohmann transfer, the path that minimizes energy, also maximizes time in the most dangerous radiation environment the crew will encounter. The cancer risk does not disappear when the spacecraft re-enters Earth's atmosphere. It is already written into the biology of everyone who made the trip, accumulating over 14 to 16 months of combined transit time. After 18 months on Mars's surface in 38% gravity, followed by 7 months in the weightlessness of deep space, the body returning to Earth is not the body that left. The changes are not dramatic in the way a broken bone is dramatic. They accumulate quietly, system by system, over months and years, and they compound. By the time re-entry begins, the crew is not simply tired. They are physiologically different in ways that make the final hours of the mission among the most physically demanding of the entire journey. The most familiar comparison is an astronaut returning from 6 months on the International Space Station. Those crews land, get helped out of the capsule, and spend weeks in rehabilitation before they can walk unassisted. Their bones have lost density, their muscles have atrophied, their cardiovascular systems have partially deconditioned because the heart does not need to work as hard in microgravity. Their sense of balance is disrupted. Their vision may have changed because the fluid in their skulls shifted forward during the mission, pressing on the optic nerve. All of that happens in 6 months of weightlessness in low Earth orbit. Now consider what happens when you replace 6 months with 25. The surface stay on Mars is not weightlessness. Mars gravity is real, and it forces the body to do something. Muscles fire, bones bear load. The cardiovascular system continues to work, but 38% of Earth's gravity is not enough to maintain the physiology that evolution built for 100%. Bone density loss on Mars is slower than in orbit, but it does not stop. Muscle mass declines at a reduced rate. The body gradually recalibrates to a world where everything weighs just over a third of what it weighed at home. After 18 months of that recalibration, the body has reorganized itself around a new normal. That new normal is not Earth. Then the crew launches from Mars, boards the return vehicle, and spends 7 months in genuine weightlessness. Whatever adaptation the surface had partially preserved now accelerates. The bone density losses that slowed on Mars begin again. The muscles that were maintained at Martian functional levels lose more ground. The cardiovascular deconditioning that the surface work partially offset resumes in full. By the time the return capsule hits Earth's atmosphere, the crew has effectively been physiologically challenged for the better part of 3 years. Re-entry is when the bill comes due. A spacecraft arriving from Mars hits the atmosphere at hypersonic velocity. The deceleration forces press the crew into their seats at several times the force of normal gravity. For a crew returning from 6 months on the space station, those forces are uncomfortable and disorienting. For a crew whose bones have spent 3 years in suboptimal loading environments and whose muscles have been fighting a slow losing battle against atrophy, that moment of re-entry is genuinely dangerous. Stress fractures are a real risk. The cardiovascular system, accustomed to pumping blood in low gravity or zero gravity, suddenly has to push blood upward against a force it has not dealt with in years. Fainting is likely. Injury is possible. The vision changes deserve particular attention. The syndrome, which NASA calls Spaceflight-associated neuroocular syndrome, has been documented in astronauts after 6-month missions. The forward shift of cerebrospinal fluid flattens the back of the eyeball, changes the focal length of the eye, and in some cases produces structural changes that do not fully reverse after return. The longer the mission, the more exposure to this fluid shift. Whether 18 months in Martian gravity partially protects against this effect or not is genuinely unknown, because no human has ever spent 18 months in Martian gravity. That uncertainty alone represents a significant medical risk that mission planners cannot yet fully model. After landing, the crew would not simply walk out of the capsule and into a recovery room. They would need to be extracted. Their vestibular systems, which govern balance, would be sending signals that no longer match the physical reality of standing upright on Earth. Their inner ears would be telling them one thing and their eyes another. Standing would feel wrong in a way that is genuinely difficult to describe from the outside. Everything would feel crushingly heavy. A hand raised against Earth's gravity would feel like raising a hand with a weight attached. The smallest physical tasks would be exhausting. Rehabilitation from a Mars mission would likely take months, possibly over a year, before any crew member could walk normally, exercise without risk, or stand without assistance. The outbound journey to Mars carries the energy of anticipation, but the return leg carries something different, something harder to manage. When a crew leaves Earth, everything is novel. The planet shrinking behind them, the first days of weightlessness, the growing silence of deep space, all of it is stimulus. The mind has somewhere to direct its attention. Mars is ahead, growing slowly larger, and the psychological architecture of anticipation keeps the crew oriented toward a future event. That orientation is protective. It gives people something to point themselves at. The return has no equivalent. The destination is familiar. The experience is behind them. What lies ahead is months of transit and a planet they have not stood on in nearly 3 years, which by the time they arrive will feel, in some ways, more foreign than Mars did on arrival. There is a specific cognitive trap that mission psychologists call third quarter phenomenon. It appears consistently in Antarctic overwintering studies, in submarine deployments, and in long-duration space station missions. The crew has passed the midpoint. The end is theoretically in sight, and that is precisely when morale deteriorates fastest. The mind registers that the goal is achievable and partially relaxes its discipline, and into that gap floods everything that has been suppressed: accumulated frustrations, unresolved tensions, the weight of 18 months of surface work and confined quarters and recycled air, and the same faces every single day. On a return trajectory from Mars, the third quarter arrives somewhere in the second month of the journey home. Earth is still roughly 5 or 6 months away. The crew has already survived the most demanding phase of the mission, and the psychological reward of completion has not yet arrived. That gap between finishing the hard part and actually being finished is where crew cohesion becomes most fragile. Communication delays make this harder in ways that are difficult to appreciate from the ground. A crew returning from Mars can be anywhere from 5 to 20 minutes of signal travel time away from Earth, depending on where the planets are in their orbits. A conversation with a family member is not a conversation. It is a message sent and a response received 40 minutes later. The emotional intimacy of real-time communication, which space station crews can still access because of their relatively close proximity to Earth, is simply not available. The crew becomes an island. What relationships exist on that spacecraft are the only ones the crew has in any functional, real-time sense. When those relationships develop fractures, and after 2+ years they will develop fractures, there is nowhere else to go. The spacecraft itself is not large. The living volume on any foreseeable crewed Mars transit vehicle is comparable to a mid-sized apartment, shared by 4 to 6 people continuously. Personal privacy becomes a managed fiction rather than a reality. Every habit, every tone of voice, every small social failure is observed and catalogued. People who were well matched psychologically at the start of a mission may find that they have exhausted their patience for each other's presence somewhere over the Martian surface, months before the return window even opened. By the time the ascent vehicle docks and the homeward trajectory is established, the crew is already carrying the full weight of everything they have been through together. There is also the paradox of proximity. As Earth grows in the cameras, the psychological distance between where the crew is and where they want to be becomes more acute, not less. The final weeks of the return are in some ways the most disorienting of the entire mission. The crew can see the destination. They know the exact number of days remaining. They have done the hard thing, and yet the spacecraft keeps moving at the same unhurried pace it has maintained for months, indifferent to how ready everyone aboard is to be somewhere else. The temptation to mentally arrive before physically arriving creates a restlessness that compounds the confinement rather than relieving it. Sleep disrupts. Appetite shifts. Small disagreements carry more charge than they should. None of this is unique to Mars. It is the pattern of every long-duration mission humans have ever attempted, scaled up by duration and distance and the absence of any possibility of extraction. Mission psychologists who have studied long-duration spaceflight consistently identify the final weeks of a return journey as among the most dangerous periods for crew cohesion, not the first weeks away from Earth. Every rocket that has ever left Earth's atmosphere has worked on the same basic principle: burn fuel, expel gas, generate thrust. The sophistication of the engineering around that principle has changed enormously over the decades. The basic physics has not. Whether it was the Saturn V carrying Apollo astronauts to the moon or a Falcon 9 delivering a satellite to orbit, the chemistry underneath it is the same story. You react two propellants together, release heat, and push exhaust out the back of a nozzle as fast as possible. The faster the exhaust moves, the more thrust you extract from every kilogram of fuel you burn. That exhaust velocity is the ceiling, and for chemical rockets, that ceiling is not very far above us. The number engineers use to measure this is called specific impulse. Think of it as the fuel efficiency rating of a rocket engine. A higher specific impulse means you get more thrust per kilogram of propellant consumed. The best chemical rocket engines flying today produce a specific impulse of roughly 380 to 460 seconds, depending on the propellant combination. Hydrogen and oxygen burned together sit near the top of that range. Methane and oxygen come in slightly lower. Both are close to the theoretical maximum for chemical combustion. There is no new chemical combination waiting to be discovered that will push these numbers dramatically higher. The physics of molecular bonds and combustion temperatures sets a hard ceiling, and the best engines in service today are already approaching it. This is not an engineering failure. It is a physical limit. That limit translates directly into transit time. To get a spacecraft from Earth's orbit to Mars's orbit in 7 months, you need a specific amount of energy delivered at departure. Chemical rockets can provide that energy. What they cannot do is provide enough additional energy within any practical fuel mass budget to cut the journey to 2 months or 3 months. The relationship between transit speed and energy requirements is not linear. It is steep. Doubling your speed does not double your fuel requirement. It multiplies it by a factor that quickly makes the rocket mathematically absurd. More fuel than mass, more mass than any conceivable launcher can carry. Engineers call this the tyranny of the rocket equation, and it is one of the most persistent constraints in all of spaceflight. This is why the 7 to 9 month transit time for Mars is not a problem that better manufacturing or smarter engineering will straightforwardly fix. It is the answer chemical propulsion gives when you ask it how fast it can move between these two planets. You can optimize the trajectory within a given launch window. You can reduce the spacecraft's mass to extract a small improvement. You cannot change the fundamental energy budget that chemistry allows. SpaceX designed Starship around methane and oxygen, and that choice was not made casually. Methane produces a specific impulse only modestly lower than hydrogen, but it has practical advantages that matter enormously for a Mars mission. It can be stored at much less extreme temperatures than liquid hydrogen, which boils at minus 253 degrees Celsius and is notoriously difficult to keep cold over a long mission. Methane is denser, easier to handle, and compatible with simpler engine designs. Most importantly, methane can potentially be manufactured on Mars. The Martian atmosphere is roughly 95% carbon dioxide. Combine that carbon dioxide with hydrogen, which could be extracted from water ice on Mars, and a chemical process called the Sabatier reaction produces methane and water. That process was a central part of the engineering rationale for choosing methane as Starship's propellant. The return fuel does not have to come from Earth. In principle, it can be made on Mars, which changes the mass economics of the mission profoundly. A vehicle that can manufacture its own return propellant on the surface of another planet is a different kind of spacecraft than one that has to carry everything it needs from the beginning. The vehicle itself can be lighter at departure because it is not carrying return fuel across 250 million miles of interplanetary space. It arrives, refuels, and leaves. This is the architecture Starship was designed around. Whether the ISRU equipment to make that work will be operational in time for any given mission is a separate question, one that involves years of pre-positioned hardware and testing. But the propellant choice was made with that eventual capability in mind. None of this changes the transit time. A Starship burning Methalox on a Hohmann transfer to Mars still takes 7 months to get there and 7 months to get back. The choice of propellant and the size of the vehicle affect the economics and the mission architecture. They do not rewrite the orbital mechanics. Chemical propulsion got us to the Moon and has sent dozens of robotic probes to Mars, but for a crewed round trip, it demands the long transit times and the long surface weights that make the 3-year mission the baseline rather than the exception. The most direct path to a faster return from Mars is not a better chemical rocket, it is a fundamentally different kind of engine. Chemical propulsion works by burning fuel and releasing energy through combustion. The product of that combustion is hot gas, and hot gas pushed out a nozzle creates thrust. The problem is that combustion has a ceiling. There is only so much energy locked inside a chemical bond, and once you have extracted it, there is nothing left to improve. Nuclear thermal propulsion breaks through that ceiling entirely because the energy source is no longer a chemical reaction. It is a nuclear reactor. The basic principle is straightforward. A nuclear reactor generates heat through fission, the splitting of heavy atomic nuclei, typically uranium. In a nuclear thermal rocket, that heat is transferred directly to a liquid propellant, almost always liquid hydrogen, which is forced through the reactor core and heated to temperatures far beyond what any combustion process can reach. The superheated hydrogen then expands violently and is expelled through a nozzle, producing thrust. No burning, no oxidizer, just an enormous amount of heat applied to a very light gas moving very fast. The exhaust velocity of that hydrogen is roughly twice what a chemical rocket achieves. In rocketry, exhaust velocity is everything. It determines specific impulse, which is the measure of how efficiently an engine uses its propellant. Double the exhaust velocity and you fundamentally change what is possible with a given amount of fuel. For a Mars mission, the practical consequence is significant. A chemical rocket on a Hohmann transfer takes somewhere between 7 and 9 months to reach Mars. A nuclear thermal rocket, using the same orbital mechanics but with its superior specific impulse, can execute the trajectory more aggressively and potentially cut that transit time down to 4 or 5 months each way. That is not a marginal improvement. That is months stripped from both legs of a 3-year mission, months during which the crew is absorbing radiation and losing bone density in deep space. Nuclear thermal propulsion is not a new idea. The United States ran a serious development program called NERVA, Nuclear Engine for Rocket Vehicle Application, through the 1960s and into the early 1970s. NERVA engines were built and ground tested. They ran. They produced thrust at specific impulse levels that no chemical engine has matched before or since. The program was cancelled in 1972, not because the engines failed, but because the political appetite for a Mars mission evaporated after Apollo, and without a destination, there was no case for the propulsion system. The hardware was real. The performance was demonstrated. Then it stopped. 50 years later, the technology is being revived. NASA has active NTP development programs running, the most prominent of which involves a collaboration with DARPA under a project called DRACO, the demonstration rocket for agile cislunar operations. The goal is to build and fly a nuclear thermal engine in space, not just test it on the ground. That demonstration flight, if it proceeds on schedule, would be the first time a nuclear rocket engine has operated in space and would provide the validation data needed to design a crewed Mars propulsion system around the technology. The timeline is aggressive. The engineering challenges are real, but the program exists, it is funded, and it is moving. International interest has followed. The French research agency CEA launched a feasibility study called Alumni in 2023, working alongside Ariane Group and Framatome under a contract with the European Space Agency. The fact that Europe is studying nuclear thermal propulsion seriously, rather than leaving it entirely to NASA, signals that the space community as a whole has accepted that chemical rockets are insufficient for efficient crewed Mars missions. The physics are the same regardless of who does the engineering. The political and safety challenges are not trivial. A nuclear reactor launched on a rocket carries obvious public concern, and the memory of accidents involving radioactive material in space has never fully faded. The reactor in an NTP system is not active at launch. It only begins operating once the spacecraft is safely in orbit. But explaining that distinction to a public skeptical of anything nuclear requires sustained effort that space agencies have historically underestimated. Regulatory frameworks for launching fissile material into orbit are incomplete in most jurisdictions, and the international treaties governing nuclear material in space were written in an era when no one seriously expected a nuclear rocket engine to fly. None of those obstacles are insurmountable. They are the kind of political and engineering problems that yield to sustained pressure, funding, and time. NTP would not eliminate the surface weight for orbital alignment, but it would cut months off both the outbound and return legs, reducing the total mission duration and the cumulative radiation dose in the process. In 2031, a rare alignment of Earth, Mars, and a specific point in the solar system's geometry creates a window for Mars missions dramatically faster than anything the standard Hohmann transfer allows. Not faster by days, faster by months. The kind of difference that changes the entire structure of a mission. The discovery did not come from Mars mission planners working forward from propulsion specs. It came from researchers studying asteroid orbital data. When scientists mapped the trajectory of asteroid 2001 CA21, they noticed something in its path through the inner solar system. The orbital plane of that asteroid, combined with the planetary geometry of 2031, described a transfer arc between Earth and Mars that had no business being as short as it was. When the numbers were checked against the positions of the two planets in that year, the alignment held. The geometry was real. What the analysis found was this: a spacecraft departing Earth on April 20th, 2031, traveling at roughly 27 kilometers per second, would reach Mars in 33 days. Not 7 months, 33 days. The crew would spend approximately 30 days on the surface, then depart on June 22nd, and arrive back at Earth by late September. Total round-trip time, 153 days, just over 5 months for the entire mission, including the surface stay. To understand why this matters, hold the standard mission timeline in mind. A conventional Hohmann transfer takes roughly 7 months to reach Mars, demands a surface stay of 14 to 18 months while waiting for orbital alignment, and then requires another 7 months to return. The total runs to nearly 3 years. The 2031 extreme case compresses that to 5 months. It does not just shorten the transit legs, it eliminates the long surface wait almost entirely. There is a second, more conservative configuration that the same analysis identified. A spacecraft departing slightly differently could reach Mars in 56 days, spend 35 days on the surface, and return in 135 days. Total mission duration, 226 days, or about 7.5 months. This version is still far shorter than any conventional Mars mission. And it arrives at Mars and returns to Earth at lower speeds than the extreme case, which matters enormously for what the spacecraft and crew have to survive. Both configurations are real. Both emerge from the same orbital geometry of that year. What makes 2031 different from other years comes down to a specific convergence. Mars oppositions, the moments when Earth and Mars are closest in their orbits, happen roughly every 26 months. But not all oppositions are equal. The eccentricity of Mars's orbit means some oppositions bring the planets considerably closer than others. The 2031 opposition is among the more favorable in the coming decade. That alone is not enough to produce 33-day transits. The additional factor is the orientation of the transfer arc relative to the orbital planes involved. The geometry of that particular year aligns in a way that allows a much more direct trajectory, one that requires high departure velocity, but pays off in dramatically shorter travel time. When researchers tested other opposition years, 2027, 2029 and others, the same trajectory options were not available. The 2031 alignment appears to be the only year in the near future where these fast transit configurations are geometrically accessible. That specificity is worth sitting with. This is not a general property of Mars travel that applies across multiple windows. It is 1 year. A crew that misses the 2031 departure dates does not simply catch the next window with similar options. They wait, and the fast configurations may not reappear for decades, if at all within any reasonable planning horizon. The implications run in two directions. For missions using current or near-future chemical propulsion, the 2031 window likely remains out of reach. The departure velocities required are extreme, and the thermal loads on return exceed anything currently flying. But for nuclear thermal propulsion systems, if any reach operational readiness by the end of this decade, 2031 represents something close to a test case that the solar system is offering once. A mission architecture built around the 226-day conservative version might be achievable with advanced chemical systems if every component performs at the edge of its design envelope. The 153-day extreme case almost certainly requires propulsion and heat shield technology that does not yet exist in operational hardware. None of that changes the underlying physics. The window will open whether or not anything is ready to use it. The planets do not wait for development programs to finish. The 2031 window is not a trick or an approximation. The mathematics are solid, the trajectories are real, and the question is only whether humanity will have spacecraft capable of flying them. Every minute shaved off the return journey from Mars comes at a physical cost that scales faster than intuition suggests. The 2031 trajectories are real, the mathematics are solid, but knowing a path exists and being able to fly it are two entirely different things, and the gap between those two statements is where the engineering lives. The 56-day outbound trajectory in the 2031 window arrives at Mars moving at 16.6 kilometers per second. The return leg hits Earth's atmosphere at 15.1 kilometers per second. Those numbers need to be held carefully in the mind for a moment, because they represent something important. A standard Hohmann transfer arrival at Mars comes in at roughly 5 to 6 kilometers per second relative to the planet. The fast trajectory nearly triples that. The spacecraft is not simply going faster, it is entering an entirely different physical regime. Consider what 15.1 kilometers per second means for a vehicle returning to Earth. The Apollo capsules re-entered at about 11 kilometers per second after coming back from the Moon, the fastest re-entry ever survived by a crewed spacecraft. At 15.1 kilometers per second, a returning Mars crew would be hitting Earth's upper atmosphere at speeds that generate heating rates far beyond anything Apollo encountered. The heat shield temperatures at Apollo return were already extreme, pushing the edge of materials technology in the 1960s. The materials required to survive a 15.1 kilometer per second entry are not refinements of what Apollo used. They represent a different category of problem entirely. Thermal protection is only one dimension of the challenge. Structural loads during a high-speed atmospheric entry scale with the square of velocity. More than double the entry speed, and the forces on the vehicle increase by a factor that does not forgive engineering margins cut too close. The spacecraft that flew a standard Hohmann return, engineered for 5 or 6 kilometers per second at Mars arrival, could not simply be reinforced to handle the fast trajectory. It would need to be redesigned from the hull outward. Then there is the propulsion side, which carries its own compounding logic. The reason faster trajectories require so much more energy is not mysterious. You are fighting the orbital mechanics that the Hohmann transfer uses to its advantage. A Hohmann transfer coasts most of the way, letting the sun's gravity do the work. A 56-day outbound flight cannot coast. It requires sustained thrust at the beginning to reach a much higher departure velocity, and then again at Mars arrival to slow down enough to achieve orbit or landing. That additional velocity has to come from somewhere. It comes from fuel. More fuel means more mass at launch, which requires more thrust to accelerate, which requires more fuel still. This is the tyranny of the rocket equation. The relationship between mass, velocity change, and fuel is exponential, not linear. Every additional kilometer per second of departure velocity roughly doubles the fuel requirement. By the time you are engineering for the fast 2031 trajectory with chemical propulsion, the fuel mass becomes a number that makes the mission practically incoherent with current launch systems. This is why nuclear thermal propulsion appears in every serious discussion of fast Mars missions. Chemical rockets hit a wall. The energy density of methane and oxygen or hydrogen and oxygen sets a ceiling on what is achievable in any mass-efficient way, and the fast trajectories sit above that ceiling. Nuclear thermal propulsion has roughly twice the specific impulse of the best chemical engines. That is not a small advantage. It means you can carry significantly less propellant mass for the same velocity change, which cascades through the entire mission architecture and makes the fast trajectories at least physically approachable. But nuclear thermal propulsion does not yet exist in an operational form for crewed spacecraft. The technology is understood. The physics have been tested in ground demonstrations. Flying it with humans aboard is another matter. There is also a subtler problem that rarely gets mentioned. The 56-day trajectory does not merely demand harder materials and more powerful engines. It compresses every phase of the mission in ways that remove margin. A standard transit of 7 months gives crews time to catch emerging problems, gives ground controllers time to analyze and respond, gives the spacecraft time to be diagnosed and managed across the communication delay. A 56-day sprint to Mars leaves almost no room for any of that. Systems failures that would be manageable on a slow trajectory become critical faster than the crew can respond. The margin that slow missions carry almost invisibly disappears. What the 2031 window reveals is a real possibility that sits just past the frontier of current engineering. Not far past it, close enough that serious researchers are studying it with serious resources. But past it. The 153-day round trip to Mars is not impossible, but the materials and propulsion systems it requires are sitting at the edge of what engineers can currently describe on paper, let alone manufacture and test. One of the fundamental constraints on returning from Mars is the fuel required to leave it. The most elegant solution to that problem is not to bring the fuel at all. The mass problem with returning from Mars is almost circular in its brutality. To launch a crew off the Martian surface, you need a rocket. That rocket needs propellant. Propellant is heavy. Carrying that propellant from Earth to Mars means launching it from Earth's gravity well first. That requires more propellant, which requires a larger rocket, which costs more to launch. Engineers call this the tyranny of the rocket equation. On a Mars return mission, the tyranny is severe. Estimates suggest that a fully fueled Mars Ascent Vehicle, if all its propellant had to be delivered from Earth, would require launching somewhere in the range of 30 to 40 tons of propellant from our planet just to enable a crew of 4 to reach Mars orbit. The numbers become almost absurd when you work backward through the chain. The alternative is to make the fuel on Mars. The Martian atmosphere is 95% carbon dioxide. Thin, yes. The surface pressure is less than 1% of Earth's. But there is enough of it. If you have carbon dioxide and hydrogen, you can run a chemical reaction called the Sabatier process. Carbon dioxide and hydrogen react under heat and pressure in the presence of a catalyst to produce methane and water. The methane is rocket fuel. The water can be electrolyzed to produce oxygen, which serves as the oxidizer. Methane and liquid oxygen together, methalox, is exactly the propellant combination SpaceX designed Starship to burn. This is not a coincidence. The Sabatier reaction has been known since the 19th century. Running it on the surface of Mars is a different engineering challenge from running it in a laboratory, but the chemistry does not change. The carbon dioxide is free and abundant. The hydrogen is the harder piece. It can be brought from Earth, extracted from subsurface ice if accessible, or recovered from the water the reaction itself produces. Each approach has complications. Bringing hydrogen from Earth partially defeats the purpose. Extracting it from ice requires knowing where usable ice deposits are and having the equipment to access them. Recovering it from the reaction's water output closes the loop, but requires electrolysis systems that add complexity and power demands. In April 2021, NASA's Perseverance rover carried a small gold box-sized instrument to Mars called MOXIE, Mars Oxygen In-situ Resource Utilization Experiment. MOXIE did one thing. It took carbon dioxide from the Martian atmosphere and converted it to oxygen using solid oxide electrolysis. On its first run, it produced 5 grams of oxygen. That is roughly enough for 10 minutes of breathing. What it proved was not a breathing supply. It proved the principle worked on Mars, in Martian conditions, with Martian atmosphere running through a real machine. Over the course of its operational life, MOXIE ran multiple times and consistently demonstrated that oxygen production on the Martian surface was not theoretical. The MOXIE experiment was a proof of concept. A system scaled up to produce propellant for a crewed return mission would need to be orders of magnitude larger. Running continuously for a year, an ISRU plant of sufficient scale could theoretically produce the several tons of liquid oxygen needed for a Mars ascent. The methane side of the equation requires the hydrogen source to be resolved, but the oxygen production pathway is demonstrated. Here is the problem that no engineering elegance can fully dissolve. The ISRU equipment has to be on Mars, operating correctly years before the crew leaves Earth. If the plant arrives damaged, or lands in the wrong location, or fails after 6 months of operation, or produces propellant at half the expected rate, the mission timeline collapses. The crew cannot launch from Earth until the propellant tanks at Mars are verified full. This is the chicken and egg constraint that sits underneath every optimistic ISRU calculation. You cannot rely on fuel that has not been confirmed to exist. Uncrewed cargo missions running years ahead of the human departure must deliver the plant, power it up, operate it through multiple production cycles before anyone boards an Earth launch vehicle. ISRU transforms Mars from a destination where every kilogram of return propellant must be launched from Earth into a place that can, in principle, sustain its own departure capability, but only if the equipment to do that has been working reliably for years before any crew arrives. Before any crew can begin the return journey from Mars, they need a way off the surface. The vehicle designed to provide that escape is arguably the most important single piece of hardware in the entire mission. Every other system on a crewed Mars mission has some margin for degradation. A habitat module can develop a slow leak and be patched. A power system can lose efficiency and still keep the lights on. Navigation software can be updated from Earth. The Mars Ascent Vehicle has none of that flexibility. It has one job, it has to perform that job at a precise moment. Failure is not a category the mission can survive. This is why engineers who study crewed Mars architectures consistently identify the MAV as the single highest risk item in the entire stack. The vehicle itself is not enormous by rocket standards. Mars has roughly 38% of Earth's gravitational pull. That means the energy required to reach orbit is substantially lower than launching from Earth. A smaller rocket can do the job, but smaller does not mean simple, and Mars introduces a complication the Moon does not. The lunar surface sits under a near-perfect vacuum. A rocket leaving the Moon has no atmosphere to fight through. Mars has one, thin but real. The Martian atmosphere is roughly 1% the density of Earth's. That is too thin to provide meaningful aerodynamic lift, but thick enough to generate drag during ascent. The MAV has to push through that resistance while simultaneously building the velocity needed to reach orbit. The design has to account for both, and the engineering margins are tight. The vehicle also has to reach a very specific destination, not just orbit in some general sense. Mars orbit is a large place. A transfer spacecraft or Earth return vehicle will be waiting at a particular altitude and inclination, traveling at a particular velocity. The MAV has to match that orbit closely enough for a rendezvous to occur, within a window that the orbital mechanics of the return trajectory define. Miss that rendezvous, and the crew is in orbit around Mars with no way to complete the transfer home and a diminishing supply of consumables. Because the stakes are this extreme, no serious Mars mission architecture sends the MAV with the crew. The vehicle lands on Mars years ahead of the astronauts, either in the same cargo sequence that delivers the habitat and power systems, or on a dedicated uncrewed mission timed to an earlier launch window. Engineers on Earth can then confirm the vehicle survived the landing, run diagnostics on its systems, verify it is ready before the crew ever boards their Earth departure rocket. If something is wrong with the MAV, the crew mission can be delayed to the next launch window 26 months later. That delay is painful and expensive. It is also far preferable to the alternative. Fueling the MAV is where the previous section's ISRU discussion becomes immediately practical. A fully fueled MAV launched from Earth is an enormous mass penalty for the cargo mission delivering it. The vehicle has to carry enough propellant to complete the ascent, execute any necessary orbital corrections, support the crew through rendezvous. If that propellant is produced on Mars from atmospheric carbon dioxide and stored hydrogen, the cargo mission can deliver a lighter, unfueled vehicle and let the ISRU equipment fill it over the years before the crew arrives. This is not a convenience. For mission architectures that depend on minimizing the mass launched from Earth, ISRU-produced propellant is what makes the MAV concept physically workable at all. The rendezvous itself is an event that has never been attempted in another planet's orbit. Earth orbit rendezvous is routine at this point. Lunar orbit rendezvous was demonstrated during Apollo. Mars orbit rendezvous would require all of the same precision, executed by a crew that has been living in partial gravity for well over a year, operating hardware that has sat on the Martian surface for potentially multiple years, communicating with Earth through a delay that makes real-time ground support impossible. Every maneuver has to be planned in advance. Every contingency has to be anticipated before the crew is already in the ascent vehicle waiting for ignition. The Mars Ascent Vehicle has to work the first time, every time. There is no repair mission, no rescue launch, no alternative if the engine fails to ignite on the morning the return window opens. A Mars mission that ends with a successful return to Earth does not begin with a crew leaving Earth. It begins years earlier with a series of uncrewed cargo deliveries that must all succeed. The sequencing is not optional. There is no version of a crewed Mars mission where the crew arrives first and figures out logistics on the ground. Every critical component of the return, the Mars Ascent Vehicle, the fuel to launch it, the habitat that keeps the crew alive for 18 months, the power systems that run all of it, has to be confirmed operational on the Martian surface before a single astronaut boards a spacecraft at Earth. The consequence of getting this backwards is not a difficult situation. It is a death sentence. This means the actual timeline of a Mars return mission begins not with a launch, but with a planning cycle that looks back across multiple 26-month windows and works out exactly which cargo needs to arrive at which window to build up a functioning surface before the crew follows. A mission targeting a 2039 crew departure might require cargo shipped in 2033, 2035, 2037, just to have the infrastructure ready in time. Each of those windows represents a narrow few months in which a cargo spacecraft must leave Earth, survive a 7-month transit, land intact on Mars. None of those events are guaranteed. The first wave of cargo typically carries the heaviest infrastructure. Power systems have to go early because nearly everything else depends on them. An ISRU plant producing methane and oxygen from Martian atmosphere requires electricity to run. The habitat requires electricity for life support. The communications equipment, the science instruments, the equipment for processing water from subsurface ice. All of it sits dormant without a reliable power source already functioning. This is not a detail that engineers can address after arrival. It is the foundation every other system rests on. The ISRU equipment itself has its own timeline problem. Producing enough methane and liquid oxygen to fuel a Mars Ascent Vehicle launch is not a fast process. Estimates suggest the propellant production timeline for a crewed mission could require the ISRU plant to operate for somewhere between 12 and 24 months before the crew even arrives. That means the production equipment has to land at one launch window, begin operating immediately, accumulate propellant through the next window and beyond. If the plant lands but fails to reach full operational capacity, mission controllers on Earth face a hard choice. They can send a replacement unit in the next window and delay the crew, or they can proceed with an inadequately fueled ascent vehicle, which is not really a choice at all. The Mars Ascent Vehicle itself arrives as cargo. It lands on the surface without a crew, goes through automated checkouts, sits fueled and ready, sometimes for years, waiting for the crew to arrive and use it. This creates a specific kind of engineering challenge. The MAV cannot be a fragile system that requires human hands to maintain. It has to survive the thermal cycling of Martian nights, the abrasive dust that works into every joint and seal. The radiation environment, without degrading over the years, it may sit before the crew arrives. A vehicle that was ready in 2037 may not be needed until 2039. Every month it sits on the surface is a month of accumulated wear. Consider what a single cargo mission failure means in this sequence. A landing failure that destroys the habitat module does not delay the crew mission by weeks. It delays it by 26 months. This was because that is when the next window opens and a replacement can be sent. If the replacement then has to be confirmed functional before the crew can depart, the actual crew delay stretches further. A chain of 2 failed landings across consecutive windows pushes the crew mission back by years. Mission architects account for this through redundancy, sending backups of critical systems on separate spacecraft so that no single failure is mission-ending. But redundancy multiplies the number of launches required. More launches mean more opportunities for failure. The logistics compound quickly. None of this complexity is visible in the final image of a spacecraft lifting off from Earth with a crew aboard. What is invisible is the years of quiet, methodical work that preceded it, the cargo ships that left in earlier windows, the automated systems that spent years producing fuel, the habitat that had already weathered a dozen dust storms before human hands ever touched it. By the time astronauts board their Earth departure vehicle, the Mars surface they are heading toward will already have been populated for years by machines whose job was to make the return possible. If an astronaut on the International Space Station has a medical emergency, they can be back on Earth in a few hours. The ride home takes roughly 3.5 hours from undocking to touchdown. This is not a coincidence of mission design. It is a deliberate safety architecture built around the assumption that fast rescue is possible. On a Mars mission, that assumption disappears entirely. The Apollo program had a version of this safety net. If something went wrong on the way to the moon, a free return trajectory meant the spacecraft could loop around the moon and coast back to Earth without burning any additional fuel. Apollo 13 used exactly this. An explosion crippled the service module 2 days out, and the crew rode the moon's gravity around and came home. The whole emergency lasted 6 days. That option exists because the moon is close, roughly 250,000 miles away, a distance light covers in just over a second. Mars at its nearest is roughly 140 times further. The physics that made Apollo 13 survivable do not scale. Free return trajectories do exist for Mars missions. A spacecraft on a Hohmann transfer to Mars that needs to abort cannot simply reverse course. It is already moving along an elliptical arc, and reversing that arc requires more fuel than most mission designs carry. A free return from a Mars trajectory instead curves the spacecraft around Mars, if it gets that far, and then arcs back toward Earth along a path the orbital geometry permits. The timeline for that journey is not measured in days. Depending on where in the transit the abort occurs, the crew could spend another 8 to 12 months in space before reaching Earth. They would be returning from an emergency on a trajectory nearly as long as the original mission. Earlier in the outbound leg, the situation is somewhat different but not much better. There is a period early in the Mars transit, while Earth is still relatively close, where a high-energy burn could in theory turn the spacecraft around. The fuel cost is extreme. The window is short. And even in the best version of that scenario, the return takes weeks rather than days, not hours. The further the spacecraft travels from Earth, the more that window closes. At some point in the outbound journey, roughly a third of the way to Mars, no practical abort option returns the crew home quickly. From that point forward, the mission either continues to Mars or the crew rides whatever trajectory is available for as long as it takes. One trajectory option that has received serious study involves a Venus gravity assist. If a spacecraft misses its chance at Mars or needs to abort without enough fuel to return directly to Earth, Venus sits in a position where its gravity can be used to redirect the spacecraft homeward. The geometry does not always cooperate, but in some mission windows the option exists. What it involves is a long loop out toward Venus, a gravity-assisted swing around the planet, and then a return arc to Earth. The total time for this kind of abort has been estimated at roughly 2 years in some scenarios. The spacecraft would pass close to Venus, a planet with surface temperatures above 460 degrees Celsius and atmospheric pressure that would crush an unprotected human being. But that detail is irrelevant since the crew stays inside the spacecraft. What matters is the timeline. A 2-year emergency return is not a rescue. It is a survival problem. The thermal environment near Venus also matters. A spacecraft swinging past Venus is closer to the Sun than at any other point in the mission. Solar panels may overheat. Thermal regulation systems designed for the cold of interplanetary space demands they were not sized for. These are solvable engineering problems in principle, but they add mass and complexity to a vehicle that already has none to spare. What makes the Mars abort problem genuinely different from anything in the history of human spaceflight is its irreversibility. Every mission humans have flown until now has had some version of a door. Orbit is close to Earth. The Moon is reachable in days. Even the furthest humans have travelled, the lunar surface, was only 3 days from home. Mars removes that door entirely. There is no cavalry, no backup capsule waiting in orbit, no mission control workaround that brings a crew home fast. The distances involved mean that any emergency becomes a long-duration problem regardless of its urgency. Every Mars mission architecture that has ever been seriously studied includes abort analysis, and the honest conclusion of that analysis is always the same. Once you commit to the outbound trajectory, you are committed. If the question is whether a crew launched from Earth today could return from Mars, the answer is no, and understanding why reveals exactly what separates where we are from where we need to be. Start with propulsion. The most capable rocket humanity has built right now is SpaceX's Starship, and it is genuinely impressive. It burns methane and liquid oxygen. It is designed to be reusable, and its payload capacity dwarfs anything that has flown before it. On paper, It is the vehicle most seriously discussed for a crewed Mars mission, but Starship has not yet completed a crewed orbital mission. It has not demonstrated in-space refueling at scale. It has not been tested in the thermal and radiation environment of deep interplanetary space for 7 months at a stretch. The vehicle is real. The operational version that could carry humans to Mars and support a return is not. Then there is the Mars Ascent Vehicle. This is the rocket that would sit on the Martian surface, waiting for the crew, ready to lift them into orbit when the return window opens. It does not exist. Not in prototype form, not in detailed final design. NASA has studied configurations. Proposals have been published, but no ascent vehicle has been built, tested in a relevant environment, or demonstrated the kind of reliability that a piece of hardware needs when it is the only way off another planet. And because the MAVE must arrive at Mars years before the crew does, the absence of a completed design today means no operational vehicle could be pre-positioned in time for any near-term crewed mission. The fuel situation compounds this. A Mars Ascent Vehicle needs propellant. The elegant solution is to manufacture that propellant on Mars using the carbon dioxide in its atmosphere, the process called ISRU. The Perseverance rover demonstrated oxygen production on a small scale with its MOXIE experiment. That was a meaningful proof of concept. What it was not was a full-scale propellant production system capable of fueling a rocket, building one, landing it intact, operating it autonomously in Martian conditions for the years required to stockpile ascent propellant. None of that has been done. The technology is understood in principle. The hardware that would actually do the job does not yet exist in operational form. Radiation shielding is partial at best. Current spacecraft materials provide meaningful protection against solar energetic particle events, which are intense but relatively short. They do not adequately shield against galactic cosmic rays, the high-energy particles streaming in from outside the solar system that penetrate most barriers and accumulate dose throughout every day of transit. Research is ongoing. Some shielding concepts show promise. None are ready to integrate into a crewed Mars spacecraft. A crew flying today would absorb radiation doses during transit that current career limits for astronauts were not designed to accommodate for a 3-year mission. The health countermeasures for this duration are similarly incomplete. Astronauts returning from 6-month stays on the International Space Station require months of rehabilitation. Mars missions involve 18 months in Martian gravity, 38% of Earth's pull, preceded and followed by deep space transit in zero gravity. The cardiovascular deconditioning, bone loss, muscle atrophy, and vision changes that accumulate over that timeline exceed anything that has been studied in practice. Exercise countermeasures developed for the space station are not sufficient. New protocols are being researched. The evidence base for what actually works at this duration simply does not exist yet, because no human has ever been gone that long. Each of these gaps is significant on its own. What makes the situation more serious is that they are not independent problems. The MAV depends on ISRU. The ISRU equipment must be delivered by a capable heavy launch system. The crew vehicle must be validated for long-duration deep space flight. The radiation environment during transit shapes the health protocols. The health protocols depend on countermeasures that have to be tested on long-duration missions that have not yet flown. These dependencies stack, and closing one without the others does not produce a mission that can return its crew safely. The realistic timeline, based on current development programs, points toward the mid-2030s at the earliest for a first crewed Mars mission. and that assumes sustained funding, no major failures in development, and successful validation of systems that are still being designed. NASA's internal planning targets the late 2030s. SpaceX has stated more aggressive ambitions, though the engineering prerequisites are the same regardless of who is doing the counting. A first crewed landing in 2035 to 2040 means a first crewed return somewhere between 2038 and 2043, accounting for the full mission duration. NASA's target of the late 2030s and SpaceX's more aggressive internal timelines both acknowledge the same reality. The return journey from Mars is not a propulsion problem. It is a systems integration problem of the highest order. The return from Mars ends not with a celebration, but with a splashdown or a touchdown, a physical event that a body weakened by 3 years of partial and zero gravity experiences as something close to violence. The capsule hits the upper atmosphere at speeds that generate temperatures measured in thousands of degrees. The heat shield absorbs that energy. The crew absorbs the deceleration. A body that spent 18 months in Martian gravity, then 7 more months in the weightlessness of deep space, meets full Earth gravity again in a matter of minutes. The forces involved are not extreme by engineering standards. By biological standards for these particular bodies, they are considerable. Before any of that, there is the fireball. From the ground, a returning Mars capsule looks like a meteor, a streak of light burning across the sky, visible for hundreds of miles. Anyone watching from below has no way of knowing what is inside. To them, it is just a bright object falling very fast. Inside, the crew is experiencing something that cannot be fully prepared for in training, because no simulation can replicate 3 years of accumulated physical change. The inner ear has recalibrated. The cardiovascular system has adapted to demands that no longer apply. Bones carry less mass than they did at departure. The planet pulling on them now is the one they grew up on, and it does not feel like home yet. It feels like pressure. The splashdown, or the touchdown on land depending on mission design, is the end of the journey in a technical sense. Recovery teams reach the capsule within minutes. The crew is helped out rather than walking out. This is expected. Astronauts returning from 6 months on the space station often cannot walk unassisted for hours. These crew members have been away 5 times longer, and 2/3 of that time was spent not in microgravity, but in a gravitational field that is real, that maintained some muscle function, but that allowed meaningful deterioration in all the systems the human body uses to move around on Earth. The first steps back are not triumphal. They are careful and supervised and measured. What those crew members have actually done is something with no precedent in human history. No human being has ever traveled as far. No human being has ever been as isolated from the rest of the species for as long. The Apollo astronauts were gone for less than 2 weeks. The longest single continuous space flight on record is a little over a year. A Mars crew returning to Earth has spent approximately 3 years in transit and on the surface of another world, across a distance that at its maximum stretched to more than 200 million miles. The communication delay alone, up to 24 minutes each way at maximum separation, meant that for most of the mission, they were making decisions without the possibility of real-time support from anyone. The 3-year figure is not a round number chosen for convenience. It is the product of orbital mechanics that were fixed before the solar system had planets. Earth completes one orbit every 365 days. Mars completes one orbit every 687 days. The geometry of those two orbits creates the 26-month alignment cycle, which sets the departure and return windows, which determines the minimum surface stay, which produces the total mission duration. There is no shortcut hiding in that math. The 7 months to reach Mars, the 14 to 18 months waiting on the surface, the 7 months to return, each of those numbers has a physical reason, and none of them yield easily to engineering pressure alone. Faster trajectories exist in principle. Nuclear propulsion could cut the transit times. The 2031 alignment could compress the whole mission to under a year in the most optimistic case. But those capabilities do not exist in operational form today. And even if they did, the biology of the crew returning under those faster timelines would still be profoundly altered. The radiation accumulated during faster transits is lower, which is an advantage. But the physical reality of living on another planet for any duration at all, and then climbing back into a spacecraft and crossing interplanetary space, is not something that engineering alone resolves. The question this video started with was a simple one. If we left today, how long would it take to come home from Mars? The answer, fully earned now, is approximately 3 years. But because two planets are moving around a star, and the path between them opens and closes on a clock that answers to physics rather than preference, 3 years to leave, wait, and come back from the nearest planet to our own. And the only thing harder than understanding why it takes that long is deciding to go anyway.